So I'm Aaron Dotson. I'm a faculty here at UAA in civil engineering. My background is in environmental engineering. I worked as a consultant for Malcolm Perney, who's now within Arcadis, I think without a name. And I did drinking water and wastewater work, primarily on challenging waters that had something that was more than just apply basic treatment. I then did my PhD at Arizona State looking at the interconnection between drinking water treatment plants and wastewater treatment plants, primarily wastewater's influence on drinking water with respect to nitrogenous disinfection byproducts. So I like the connection between water and wastewater directly, and thus getting into water reuse is innate in that thought process. So we'll talk about the Alaska Water Sewer Challenge, at the work done by here at UAA. We're calling our project Reuse Water Alaska, and there's two other teams involved in this that I want to just throw their name out. So Dow and CDM Smith are one other team, and Summit Consulting is the third team. We're all doing parallel projects here. So if you're interested in what they're doing, find them. You're just going to hear what I'm doing here today. So I do acknowledgments and funding up front. Otherwise, if I get excited and talk over my time, I never get to them. So thanks to DEC, as well as I think EPA, for funding this work to date and hopefully into the future. And with that, we have a very large team. When the state asked us to put together a team, I was pretty focused on trying to find the exact people that provided the niche work. Further, as an academic, I don't have a large company to delve from. I pick my company from anywhere out in the wild. So we have the university here, engineering and public health. We have three other universities here in the U.S., University of Colorado, University of North Carolina, and University of Southern California, all with specific goals in mind. Colorado is ultraviolet light. USC is membranes. We have three universities in Canada. Those three universities are part of the RESO WaterNet, which is a network of small water systems throughout Canada. UBC does innovative UV work. Dalhousie does work up in Nunavut with cold regions. And E. coli de Polytech Montreal does work throughout with a variety of other technologies. Other nonprofits, ANTHC has a small role. First Nations in Canada has a small role. Cold Climate has been helping us out with some of the house-related work. Some engineers, some of which are in the room, GV Jones, MWH, and Streamline AM, although I don't know if Streamline's really an engineer. They're more of a management group now. And then the bottom, Southern Nevada Water Authority, is our technical lab. They have a very large research lab and are capable of measuring, you name the pharmaceutical or emerging contaminant, they can measure it. So that's where we stand. On my side, we have at least two grad students in the room working on this project, Greg and Kara, and we have one from Colorado, and we'll have a bunch of other undergrads joining us too. So for those of you that may or may not know the situation, I snagged these slides from one of Bill Griffith's talks back in 2012, showing that in rural Alaska in 2012, about 6,000 homes were unserved, many of those being in unserved communities, while others were unserved within communities that had plumbing. Of these, they broke that down further into homes that could probably be funded by connected to the existing system, some that have no funding but need to be connected, and some that are just considered unserviceable, meaning the home might not be even structurally sound enough as a place to really live, and so putting in infrastructure into that home probably wouldn't be a good idea anyways. So with this, the project, the Alaska Water Sewer Challenge, evolved mostly because the funding gap between what funding is being provided to the state and what funding needs to be put out into these communities to meet the needs of the communities with respect to installing plumbing is getting bigger and bigger with time. 2013, 638 million. The last number I saw was 660 million. So it'll just keep growing, and I can only imagine it'll start growing faster as some systems fail that are being challenged right now. Beyond its initial capital cost, which most rural communities are granted their infrastructure without direct cost from them, The operation cost is left up to the communities themselves. So it's, again, working from the data that Bill put together, showing that the EPA threshold is 5% of the median household income for water and sewer services. And the dashed green line here at the bottom is the average in the lower 48, saying that, hey, Anchorage, Juneau, Sitka, Palmer, kind of around what the average in the lower 48 is, but rural villages that are listed here are much, much higher than that of even the EPA threshold. So how can we bring the monthly, annual, or monthly operating cost or bill to the consumer down? So utilities as it stands cost too much to install. Monthly costs are way higher than people can sustain. Where do we go from here? So we look to another concept looking at decentralized water, putting water in people's homes. The most classic term is kind of well and septic, but as many of you know, our conditions here in Alaska make well and septic kind of a bit of a challenge in some instances. So this project we're going to talk about today is kind of, if well and septic doesn't work and if nothing else works, this concept of water reuse has a possibility. A study done by Tim Thomas at ANTHC as well as CDC found some interesting findings that I'll try to explain. If you came to Tom Hennessy and Tim's talk earlier this semester, this will make a little more sense. But they went to 4 communities that were due to have water and sewer service installed in their community, evaluated how much water per capita per day people used in a self-haul system, and found that per capita per day in village A, B, C, and D, they used between just below less than a gallon to almost 2 gallons per capita per day. That number is about half to a third of what the World Health Organization's survival threshold is. So this is at the level of refugee camp or below is what it equates to. When they returned to these communities, they found that when the plumbed water was installed, communities A, B, and C, and D started using their water, ranging from about 22 gallons per day to just below 40 gallons per day per capita, which is good. Does anyone know the U.S. average of in-home water use? Close. My calculation is 70, based on what EPA puts out. So 70 gallons per capita per day is the average lower 48 in-home water use. So some of our communities, when you get plumbed water at your house, approach that. Community D, on the other hand, didn't change much. They increased probably 3 or 4-fold, but they didn't get up to a really high water use, primarily because what we've heard from ANTHC is that their billing structure was prohibitive and essentially made people drastically conserve water to avoid the user fees. So we're now above, even in the case of the drastically conservation, we're now at least above the WHO's survival requirement, which is a good thing. And then looking toward the Alaska Water Sewer Challenge, we are targeting 15 gallons per capita per day. So we're above Village D, but we're notably below the other villages, as well as below the national average. But it will feel, and the hope is that that amount of water, if used appropriately, would still feel like you're in a full plumbed home. It wouldn't be any different, just you have to conserve water. If you have questions along the way, feel free to just shout at me. I'm used to it with students. So taking from the Alaska Department of Conservation's website, we can take the challenges they put out as develop innovative and cost-effective water and sewer systems for homes in remote Alaskan villages. Technologies to be addressed are to be decentralized water and wastewater treatment, recycling, and water minimization systems, significantly reduce the capital and operating cost of in-home running water and sewer for rural Alaska. So that's our goal. And with that goal, they've defined 5 phases of this project. We currently are in phase 3. Phase 1 happened in 13-14, forming our teams. Phase 2, we were funded for a year. 10 teams were funded for a year to go out to, and 6 teams were funded for a year to go out to assigned communities. Ours were Kipnuk and Kayakuk, to work with them to understand how in-home water sewer from this decentralized perspective might fit. Phase 3 is where we are at now, which I'll talk about in the latter half of this presentation. And if all goes well, whatever works from phase 3, the state has the ability to pick and choose from the 3 teams that are working to make a system that could be implemented in a rural home in phase 4, and as well as refined and implemented more broadly in phase 5. So, pretty aspirational. I think this project is definitely on the national radar. We're the first to pursue something like this at the household level. Decentralized water reuse has become a pretty hot topic. City of San Francisco has pursued very hard with Water Reuse Foundation to look at it, but they are really trying to consider the reuse as just for toilet flushing, irrigation, and waters that would be reused for not human contact. And so this changes the game. This is saying, hey, we want water that's going to be in contact with somebody as they take a bath, a shower, they use it in their home for hygiene, and how might that vary from drinking water? So, any questions so far on the project background? All right. So, end of phase 2. Kind of sum up where we ended last summer and presented to the state. The state encouraged all the teams to use a model called the design thinking model, which is this, where we learn from people, we find patterns, we generate design principles, we make those design principles tangible, and then we iterate and we go back to the community. And we did exactly that. We went out to the community with no design in hand. We had ideas, we brought a bunch of items like this, my fun, wonderful stage of things I can show. We asked people questions, we identified what people would and wouldn't do, we designed something, we drew it up, we went back into the communities with our design in mind, shared that design, worked to lay out people's homes, how would they fit into the home, how would they consider our system working with them. And I think it went really well, and we presented it to the state. So what did we learn? This is my summary of a variety of the questions we had. We asked some basic ones and then some quite complex ones. First one, how many people lived in your house? Blue is, no laser, that's okay. Blue is Kayakuk, brown is Kipnuk. Less people live in homes per home in Kayakuk in the interior than out in the YK, which didn't surprise us. The YK is growing and the interior in many of rural communities is a bit shrinking. Did people leave their house in the winter and allow their house to freeze? More did in the interior than the YK, which is interesting. If you had to put a treatment system on at your house to reuse water, would you mind it being in a box outside your house? No one seemed to mind. By the way, the ones on the left are positive, the ones on the right are negative. How many showers would you take a week? We asked this question because the state in our contract had defined how many showers they wanted us to design to. That was that the house had 4 adults in it, and those adults, each of them would take 2 showers a week. So we asked, how many showers would you take as a household? And so it was interesting to see quite the difference between the 2 communities. Kayakuk didn't seem to mind having less showers than out in Kipnuk. Which the other interesting finding on this was that between these 2 communities, Kayakuk had a washateria that was very well used, and the showers were very well used. Kipnuk had a washateria that was pretty well used, but everyone also had steam baths at their house. So the fact that people wanted still more showers in Kipnuk as well as having steam baths was kind of interesting.
I have a question. Is that per capita or per household?
Per household.
Okay.
Sizing the system there is what you're talking about.
Yeah, we're trying to size the system. How much laundry would you do at your home? The state suggested we needed to put a washer and dryer, at least the fixtures for a washer and dryer in everyone's house, and said we needed to do 30 pounds of laundry a week. That didn't give us a real reference on how many loads of laundry people did and what those were, so we asked, which is pretty close between the 2 communities. Would you mind chlorinating water that was not for drinking? People seem to not mind that if you chlorinated water that you didn't have to drink. People seem to understand that chlorination did help improve water quality, but they just didn't like the taste of it. We did a great experiment. Kate Rodriguez with G.V. Jones, as well as Elizabeth Snyder Hodges of Public Health at both the schools did an experiment where we made a bunch of treated water samples, we chlorinated at different levels. I actually could not detect the difference in chlorinating between each of the water samples. The kids could arrange them exactly in order of concentration by just smelling them. So it was, I'm desensitized living in the world we live in. Next question, would you be willing to have a timed shower? In Kayakuk, people said yes. In Kipnuk, people said no. I actually have a suspicion that the no here on the timed showers was because the school in Kipnuk had a timed shower, and it was pretty contentious among the community, so they all knew what a timed shower felt like, and there was not such a thing in Kayakuk. Thinking of water reuse, as well as we'll share with you later, picking what type of soaps you use can play a drastic role in how the system might work. So would the community be willing to change their soap if the system were to require a specific soap? And generally speaking, people said yes. Would you be willing to have very poor quality flush water? People didn't seem to mind. It was about 50-50 in Kayakuk, but no one minded in Kipnuk. And the last question was, would you mind puddles around your house associated with the discharge of our treatment system? In this case, we don't know if we actually asked this question correctly. We asked around after we got our responses. The YK said they didn't mind standing water outside their house. We don't know if they actually meant that or didn't, although the YK is pretty wet anyways, so there's lots of puddles, so I don't know if another puddle would make a difference. So I don't know how much I trust that. So we learned a lot, I think, from these type of questions. There were many others, but I think these highlight the variety of answers that helped us do our design. With that, we moved on and said, all right, the state has delineated what treatment processes, or not treatment processes, what fixtures we require. Through one of our questions, many people said, hey, our house isn't big enough to have a toilet, a kitchen sink, a laundry, a bathroom sink, a shower, and whatever you need to provide drinking water. So it became very obvious that we needed to treat all of these fixtures as modules in our system. So we made them exactly that. We made them modular, and we designed them kind of independently of each other. You could have one, you could not have one. It didn't matter to the treatment system. And then outside of these modules, we had a core module. So for later on, I'll try to highlight, this is our toilet, as expected. Double sink is the kitchen sink. Washing machine, shower, bathroom sink, and the bucket with the water drop is the receptacle for our drinking water or other water, as you'll see later. So we had these 6 different fixtures that you could put in your house, and then we had one core module that would live outside of your home. The interesting thing we did with our fixtures is we had a lot of people saying, hey, you guys are going to retrofit all these fixtures into our house. That seems like a whole lot of work. Having gravity plumbing, we know gravity plumbing freezes, vacuum toilets. We had the most spectacular people share crazy stories about the excitement of using their first vacuum toilet. And so we tried to look a little different. This process isn't uncommon. In fact, if you've had beer out of a keg, you've experienced this process firsthand. But we're using air-driven plumbing for the most part. Imagine your sink, instead of going to a drain pipe, it has a vessel below your sink. Water fills in your sink, comes out of your spigot, fills this vessel here below your sink. When it fills the vessel, the vessel is vented out to the atmosphere, actually out of your house. You don't want potential sewer gases coming out of that area. Once that vessel is full, the vessel says, hey, I'm full, do something about it. It closes the tank. It allows air to enter into the tank. There's a tube that comes out, the thing that would dispense your beer into your cup, and now it's dispensing water out of this tank. It dispenses the water, exchanges it for air into the tank, sends it back out to the treatment module. Now our system is clear and ready to be reused again. The benefit of doing this, all of our plumbing on our sewer side can be very small diameter. We're pressurizing it. We're using low pressure air. It'll be about 15 psi. No gravity plumbing. The other bonus, we can blow the whole pipe dry when it's not being used. So the line headed out through the wild into another heated vessel or container could be dry. No chance for freezing if there's no water present. So I will explain not this in detail, but say that this is our process scheme artistically rendered from the first from phase 2. It's since changed, but in here we had two loops. A primary loop, which allowed drinking water within that loop to be dispensed at your kitchen sink and your bathroom sink for washing your dishes, cooking, brushing your teeth, things that you would want the water in your mouth. The secondary loop around this main one is this treated non-potable water. We called it that at the time of our first presentation, that was dispensed to your fixtures for general hygiene use, washing your hands, washing your clothes. It was then processed as gray water to a membrane system, which retreated it to be recycled in that first primary loop. Your kitchen sink water can be pretty nasty. It can have oil in it. It can have other things that you might not be able to easily treat. Is sent over to another treatment system and then recycled in a much smaller loop to allow the toilet to flush. In this system, you had to provide drinking water in at 2 gallons per day. You had to provide some other source of water of your choosing into the system at 8.6 gallons a day. You had to haul what you flushed, the full flush in your toilet at, as 2.5 gallons a day, and you had to haul the treatment waste, which is concentrated gray water, at 1 gallon a day. And then there was some excess water that was left to be dumped on the ground. The scheme's pretty complex, but we can minimize it in treatment processes, try to compact our treatment skids. But overall, you had to input 8.6 gallons a day of natural water. You had to input 2 gallons a day of drinking water, so about 11 gallons a day of water. You had to discharge 6 gallons, and you had to haul 3 gallons, and that gave you an equivalent water usage of 60 gallons per day in your household of 4. So 60 gallons a day is moving around, but in and out of the home is about 10. So you get a 6 times bump in the ability to use that water. So we had some concerns from the state and others about discharging water onto the surface. Would that cause a glacier in the winter? And it also caused some complexities doing it this way. So we continue to evolve through this phase 3 to select our treatment process. So we'll continue down that road. This is what we showed the state is what our treatment or our fixtures and our treatment process would be like. So the drinking water module that I mentioned would be a container like this in your home, built into it, what would look like a cabinet. You could open the lid, pour your drinking water in from wherever you comfortably feel you want drinking water. Blue being washateria water, pink being ice melt, snow melt, you name it, whatever you like to drink. Underneath the sink, we have a small filter for coarse filtration, something like this, which is a 1 micron filter just to take out debris. And then we have a small UV system. And so that would ensure that even if you brought water that maybe was good in every other way, but you might have contaminated it with dirty hands and had a pathogen or two in it, at least it would be safe and not get you sick tomorrow. So we're left with this.
So will the UV protect against bacteria adequately?
Bacteria is easy. So with UV, it's viruses that are hard.
Well, yeah.
So the dose on this UV device would not be suitable to handle
adenovirus.
4 log adeno. You'd probably get more like 2 out of it. It would be, this one was sized at 40 millijoules per centimeter square. So bacteria, no problem. Crypto, no problem. Giardia, no problem. Viruses, only 99% removal, not 99.99. But hopefully you're selecting your water as a homeowner appropriately and handling it well. I say that I'm not worried particularly about this system because people in rural Alaska, as well as me, when I drink water sources that are not coming out of a spigot that I trust, I'm pretty careful about where I get my water. I don't go pick water from a place that is known to be contaminated. So hopefully this will give you just a little extra assurance of treatment, but not a whole lot. The next thing we designed a little 10-foot connex to put all our treatment system in, 2 treatment vessels or devices, which is this black column and this purple column, and then some tanks, which are the barrels up on the shelf. and our air compressor all fit within the 10-foot connex that hopefully all of the things that needed to be taken out to the community to have this installed could fit there. So pack it up here in Anchorage, send it out to the community, it gets constructed. The container that it was shipped out would be the container that would house the treatment system. No backhaul required. And so we left this, we were pretty comfortable with it. And these are the two line schematics of the treatment systems that were within that housing, meaning we collected gray water, we coarse filtered it, it went through a nanofiltration system. We did have 2 UV systems in a series to achieve 4-log disinfection of viruses, and it was then stored for reuse. Black water, same thing. It was treated for reuse in the toilet, and then it was the waste product that was ready to be hauled off site in another system. So we were pretty comfortable. I think the state was comfortable enough with what we did that we moved on to the next phase 2 with this. The one thing you see mentioned that I only have one membrane. In fact, this is our membrane housing that we had in both the old design and now in my hand, so obviously it's in the new one too. This is our membrane system. Most membrane systems work in arrays where you have lots of membranes that allow you to get the recovery you're targeting. We don't have that opportunity in this case to minimize components. So what we're going to do is we're going to do this membrane concentration in a single batch. And so this figure shows that here where we have a tank of water. We draw water from that tank. The treated water goes through the membrane, which is our slash, out the other side. The water that's now concentrated by the membrane is returned to that tank. We continue to recycle, meaning that tank is getting more and more concentrated with time, and keep going. And now it delineated as red, so that water has now become too concentrated. We don't want to continue treating it anymore, and now we send it out to waste. So we try to think of like our water as a sponge, right? Our water picked up all of this debris from coming in your house. You want to get all the debris out, but you still want the water because you don't want to have to go back and haul more water from the washateria or the pond. So we squeezed that sponge, all the water out, and then we threw the sponge away. So we're still using this idea, trying to maximize our use of our membrane system. And then once the tank is empty, refill it and start over.
And how do you monitor or control it or whatever?
We're going to probably be using conductivity to look at the concentration of salt. And so the water that's being recycled, our membrane can actually reject salt to some degree. And once it gets so salty in that, we're going to get rid of it.
Trip it and dump it.
Yeah. The other thing, and we have the bottom half of it up here that we're using to help maximize use, as well as I think an impression we got from many people out in the communities was if we're going to put a toilet in our house and we're going to try to look like we have a house that could be anywhere in the world, in a developed community, we want a real toilet. We don't want a piece of plastic or a piece of metal from an airplane. We want a real toilet. So this is a toilet created in Sweden called the Eco Flush. It's a separating toilet. You're welcome to come up here and check it out after the talk. It does have 2 containers. It's not like the dual flush toilets you see in some place where you hit a big flush and there's a small flush. There's 2 flushes on here, but it actually flushes 2 different compartments. So if you've hit the urine flush, the small flush, hopefully you peed in the right hole because it only flushes this little front one. If you created solids, hopefully you did it in the back bowl and you hit the big back one and it goes out the back bowl. The flush for the urine is only 0.05 gallons per flush, so really, really small. And for a full flush, it's 0.66 gallons. In fact, a lot of people that I know in California that have been playing with these, I think they have 2 biggest problems with these. One, men don't always like to sit or aim that accurately to get into that small hole. And 2, small children are kind of challenging to get them to get it in the right place. So maybe someone needs to redesign a cool little kid seat for this. But check it out. It's been a total nightmare to get this toilet, but if this works, we should directly order them from Sweden. All right, so that's where we left off in phase 3. We were excited to get going. We knew what we designed had potential to work, but I can't sleep at night, so I continue to evolve our design. Since then, we've changed our water conveyance scheme slightly, using small independent pumps for conveyance to the fixtures, as well as still using our air-driven collection. We've associated independent filtration that resides in the home. So for each one of the fixtures, your shower, your laundry, your kitchen sink, you would have a pair of filters like this inside of your home, so that if for some reason you or one of your children dump something crazy down your sink, that you only have to fix a small, this is a $1 filter and this is a $3 filter, rather than doing the whole home equivalent filters that are like $150 each. So it provides this, hey, I just dumped the gallon of oil down the sink here, I better go get it out of my filter before it wrecks my next system. But it doesn't wreck all of your systems, just one of them. It also allows us to really keep each one of those fixtures in your home independent. If you didn't have a bathroom sink or a kitchen sink and you had a limited number of fixtures in your home, you didn't have a way oversized filtration system that cost a lot to run. The other thing we did is we were granted permission from the state to reuse, which I now term reusable black water, resulting in a design that has no surface discharge. So no puddles, no glaciers, hopefully. So I'll explain this figure a little bit clearer. This goes back to our fixtures. We bring drinking water in, we dispense it to our bathroom sink, our kitchen sink. We have a toilet, a washer, and a shower. We then use that water, we flush our toilet, it gets hauled. That's the big flush on our toilet. We then use our shower, our bathroom sink, and our washing machine. It gets sent over to our treatment, the core module, where it's treated through one of those membranes, and that membrane has a reject stream. If you were to stop here, which is totally a valid choice for a homeowner, which I can tell you there's people in anywhere that would not say like the next part of our treatment system. But if we stop here, we end up with a situation like this. You have to haul 6.5 gallons of water from your toilet and your kitchen sink on a daily basis. You have to replenish your drinking water and replenish the water that is being rejected by the treatment system. So in this instance, you bring 12 gallons a day of replacement water in, you haul 13 gallons of water, and you bring in 2 gallons of drinking water, you're good to go. Now, what we did here, and what we'll be testing here on campus, is kind of the next generation, trying to go back to the true model of making something that fits in the scheme of today's current practice. So we add a second treatment system. This is our black water treatment system. We take the small flush from the toilet and the kitchen sink, and we send it to we call that reusable black water. We send it to the first membrane system, which then it's treated. The treated water from the kitchen sink and the toilet then is treated again by a second membrane before it's reused. And in this instance, now we only have to bring 3.6 gallons of water in from any source, 2 gallons of water in for drinking water, and haul 5 gallons of water a day for waste. So now we're in the same realm that Tim Thomas identified. In a community without plumbing, people were carrying between about 1.5 gallons per day per capita. So 1.5 gallons per day per capita in a household of 4 is about 6 gallons per day. We're bringing about 6 gallons per day into this house, and we're now getting 60 gallons worth of water use. So this now doesn't change the practice of an existing community. It just increases the water available at someone's home for use. So we're totally stoked. I think I might be a little overzealous on our treatment side, but I'm hopeful, and that's the reason we're using some pretty cool industrial processes here. So this is where we stand today. This is what we're building out in the back behind the building. So things to keep in mind. Our drinking water system, we actually have it mostly built right now. We're going to use a 1 micron cartridge filter like this, a little $1 filter, and then disinfection with a 40 millijoule per centimeter squared at 2.5 GPM. This is a Viqua VT4 little UV device under the sink. It's a 20 watt light. So if you can run a 20-watt light, you can keep your water disinfected. So pretty cheap overall to run, added protection against transportation contamination due to U, and basic pathogen protection. So in our core module, we now expand into the pair of filters per fixture, our bag filter and our 1 micron cartridge filter. Provides that modularity we need, and it's accessible within the home in case it breaks. No one wants to go out and change a filter out in the shed outside if they don't have to, and so we'll put it in the home. Our membrane that we're going to be using is actually up here if you want to take a look at it. It's a nanofiltration membrane, a HydroCore 70 PHT. It's a really cool membrane. It's actually an industrial membrane made to treat far more water than what we are doing. It produces water at about 5 gallons per minute is what we're projecting right now. So this could produce a whole lot of water for your house. But the idea here would be that if power is unstable, if other things are unstable in your community, you could produce a day worth of water in about a half an hour. So you turn on the system, run it for a half an hour, you have enough water for the next day. The pore size of that membrane is 750 Dalton, pretty small. It rejects salt. The cool part is it's chlorine resistant, meaning if it gets gummed up, we can actually chlorinate the membrane. It can handle 100 parts per million of chlorine for cleaning, or 10 parts per million constantly. It's fouling resistant based on the charge on the membrane. The membrane's intention is for actually treating pretty crazy industrial compounds. And very highly colored water. So we're really hopeful with this membrane. Our UV disinfection system inside of the home is a Viqua. It doesn't really have a name. They just call it their adenovirus system. It's actually 2 Pro 20s in series. It's validated by the EPA at 4 log virus up to 15 gallons per minute. So we're going to actually get more treatment than we need. And if you think about our treatment cycle, that black water is going to go through the membrane and the UV twice. So we're going to be doing a kind of almost approaching possibly photocatalytic, or not photocatalytic, photolytic oxidation that we might have. Again, this will only be run when you're producing water. So that half hour a day, you turn on these lights, it runs, it turns back off. So I didn't have time to redraw this, so you get to look at my hand sketch. This is the hand sketch we sent to the state illustrating how our system works. We're actually going to be reusing parts in the system. We have one pump that drives both membrane systems, and we have one UV device that is being used for both systems. So what we would do is there's valves in the system to say, hey, if you're treating black water, we're going to be taking water from the liquid black water tank, using our pump, treating it with the black water membrane, passing it through the UV system, putting it in the gray water tank. If we're treating gray water, we're going to be using our same pump, passing it through our gray water system, or our gray water membrane, using the same UV, and passing it or putting it in the hygiene water tank. This allows us with the valves to keep our membranes washed with clean water. It allows us to also give a homeowner the choice of, hey, you know what? The kitchen sink and the toilet, I don't really want to deal with that in my house. So you can just, as a homeowner, select to not use this by valving out part of the system. You don't have to change the drawing.
So the homeowner is going to need to turn some valves every day?
No, all of these are automated valves. So we'll have a system built together. I'll talk about automation. So in this, as you imagine, the black water goes through all of this treatment, all the way to the hygiene tank, and the gray water only goes through a small amount. Based on the literature, we have, for black water, we have 8 to 24 log inactivation of organisms, and pathogenic 10 to 24 log. So this is 10 log is 99 and 8 more 9% removal of pathogens. So
How are you dealing with cross-connection control and the potential to interconnect parts that you don't intend to?
it's water reuse, and we're going to be flushing water that's treated through it all. So after any time you use a poorer quality water, a higher quality water will be flushed through. So we have lots of treatment. I think it's a pretty entertaining idea here. And again, this water's not for drinking, right? And so we understand there is potential and probably way against code with cross-connection rules, but this is not water that is connected to anyone else but your home, and it's not water that's intended to put in your mouth. Not to say that I probably wouldn't drink it. It would be fine. I would have enjoyed a glass of this, maybe. Although one of our tests might have showed me something entertaining. So we did some preliminary testing, not with this membrane that we have. I'm more hopeful with this membrane than the weird Chinese membrane I had in the lab. We took a little system in our lab, which is a little pump. In here we had a 1 micron cartridge filter and then a RO membrane that was not a very good one. And we treated gray water that we made. The gray water that we made was made of all this stuff. The gray water here, you can come and check out the stuff, as well as you're welcome to pass this around and you can sniff it if you so desire. The gray water is created according to the National Sanitation Foundation's NSF 350 guideline. It's a recipe. It uses all these ingredients, and that's what we treated. We concentrated it about by 50%, and up here on this plot, you can visually see this is untreated. Our experiment we did is we filtered it through a 1 micron filter, a 0.7 micron filter, a 0.22 micron filter, and then our reverse osmosis. With that, we found some pretty cool results. Hey, you know what? It meets the DEC's suggestion of less than 5 NTU turbidity. In fact, it's the lowest of our treatment bunch. It meets the DEC's target for total dissolved solids, although the source water is also below the limit for total dissolved solids. And even better, it was the only one of our treatment systems that managed to remove enough organic carbon to be below the state's goal of 10 milligrams per liter. The interesting part about this, you can check it out on our blog post too. If you open that and take a sniff, it smells like soap. It actually smells a lot like really flowery soap. When we treated it, this water smelled like peaches. We don't quite know why it smelled like peaches, but it did. We know there's still organics in it, so there's something left behind that fit through our membrane that was like that. So different membrane, we're still hoping for something, although I wouldn't be adverse to having peach odor scented water to take a shower in. The other thing we've been doing, I had an electrical engineering senior design group do some work for us where we are proposing that instead of using a centralized hot water heater in your home, again, trying to keep everything modular, each one of the fixtures that you would think about having hot water in, your shower, your bathroom sink, your kitchen sink, and your washing machine would have its own independent hot water heater. I hate when I say that, water heater. I hope we're not heating hot water anymore. Its own independent water heater. And so the thing about this is these are electric water heaters. Electricity costs a lot of money, as well as a lot of communities couldn't tolerate if you put on 4 water heaters into someone's house. So what we had this electrical engineering senior design group do is to build a circuit as well as a logic model that would allow each one of these hot water heaters to be connected into the same outlet and operate only when they needed to, as well as with priority. So if you went to take a shower and you started using the hot water, the system would direct its energy toward your shower to keep you having a hot shower. And then it would cycle through the other heaters to make sure they were all warm. And if you started using the laundry, it would then shift over to the laundry and provide its current there. And so at any given point, the system only draws 11 amps. And these heaters are pretty robust. If they just sit there on the counter, it takes about a day for them to cool off to reheat again. The other bonus about doing on fixture water heating, especially in this way, is that when we're reusing water, so I don't want someone running the water to let it warm up at the sink like I do at home. I want them, when you turn on the water, it's hot so that you can use it. And so now with this, these are 2 and 4 gallon water heaters. You turn on your bathroom sink, you'll get hot water immediately, no running it before. Although it would change the way I shower because I kind of diddle around while it warms up. So I would have to get in the shower faster, I think. All right, so this is a thing we're working on. Again, that is definitely not to code, that wiring on a piece of plywood, but we'll get there. Where are we doing this? We're doing it behind the engineering building. In fact, this is a picture taken from our lab yesterday. This cabin is going to have all the fixtures in it. This little Connex, I'd never actually seen it before I bought it. That's a little 10-foot Connex. It's kind of like a cube. Is sitting right next to it where all treatment device will be in there. The automation as well as the system control will be done using an Arduino clone. This is a Motino. You can buy one of these controllers for about $20. It's a microcontroller with a radio on it. The cool thing about this is it's based on this concept of Arduino. Arduino is used for high school robotics. That's the picture I have with kids down there. And so if you can teach high schoolers how to program one of these to run a robot, you can teach them how to program their water system in their house to make their house work. So the idea is kind of cross bridges. High school students are not going to learn how to do controls on Allen Bradley instruments. I'm just not part of high school curriculum, but exciting them to make robots, I think, is possible. So trying to blend streams. So we're using these. We actually are using them in a lot of projects. They're really kind of fun. Beyond that, they're able to talk. So you could actually reprogram them without ever unwiring something. So you can stand in front of your sink if it's not operating right and change the way it runs. So we're using these. I didn't bring one of those. If you want to see one, I can get one down here. The other thing we're doing is because we have fixtures, we're running our house like a house. So we're not having people in our house, but we're having the fixtures run like that. So this is an example of the regular loading scheme the state has prescribed and what fixture would run at what time. And so throughout the day, when you wake up in the morning, this example here, it shows that, hey, you wake up in the morning, you drink water, you take a shower, you use the bathroom sink, and you probably pee in the toilet. And so that would occur at 6 a.m., automated in our system. Down the road, it would go through these daily fixtures, our daily functions. So we have a lot of loading schemes that are prescribed by the state, and we're taking the loading schemes that are just based on hydraulic loading to a wastewater or to a treatment system and moving them into a tangible household usage pattern. Because I don't want to do a loading condition on my treatment system that is not tangible to do in our house. Like, no, I would never run my washing machine for 3 days straight. So we'll contend those type of loading schemes. The other fun one is being that we are not going to be living in this house and we're going to be recycling water. We're going to be making everything. So as you saw, we made gray water. In fact, we're going to be making gray water concentrate to amend to the water that's recycled into the home. We're going to be making a different type of gray water for our laundry, for the washing machine. We're going to be making our own recipe for what goes down the sink. We're going to be making synthetic urine. We're going to be making synthetic fecal material. And so it's all going to be this entertaining fun of us making all kinds of stuff. By the way, synthetic fecal material is dog food and not glycerin, gelatin. Dog food and gelatin. Entertaining stuff. Mainly just to figure out how to flush the toilet. Source waters around here. We're going to use local tap water to simulate washateria water. We're going to collect rainwater from the cabin itself to be used, as well as we're going to collect water out of the west, I think it's the South Fork of Chester Creek, the creek that's right here that goes under the road for part of our study as a source water for the system. So we're going to be using a variety of these. The building out there will not have plumbing to it. It will have electrical to it, but no plumbing. So all water in and out gets to be carried by some student, and possibly me, probably me. I'll at least do it a couple times.
Delegate.
Yeah. So if you want to keep track of us, go check out our website or our Facebook page. I realize those pictures are actually backwards now that I look at that. But we're trying to share, as well as we're open to any input that anyone might have. So check it out. We're trying to do weekly posts. This lecture today will be posted as one of our blog posts, as well as with a recording of it, so that anyone out there can check it out. Furthermore, if you're going to the Alaska Water and Wastewater Management Association conference next week, we have an entire day on Wednesday dedicated to water reuse. This is a pretty new topic, so I think it's advantageous to get everybody in the same room. I have two people coming in from out of state. Guy Carpenter is, I think, the current president of the Water Reuse Board. He's talking about water reuse. He's giving 2 talks in this session, as well as a lunch keynote on national water reuse. We have Chad Seidel, who works with Corona Environmental. talking about small systems and how you might be able to modify code and plumbing to make it work in a small system versus a big system. And then we have the state talking. Each of the 4 teams have a speaker, myself from UAA, Chris Schultz from CDM Smith, Park Roush from Summit, and Brian Lefferts from YKHC. YKHC is actually doing this project all on their own dime, outside of the purview of the Alaska Water Sewer Challenge. So they have running systems right now, so I'm hopeful. So you're welcome to come register for the conference. It should be pretty entertaining. With that, thank you for listening to me. And if you have any questions, I'm happy to take them.
Aaron, what's your expected life on the membrane, the RO unit? A couple of years?
Greg is smiling very brightly at me. It's probably a couple years. Although the thing that I have to kind of keep in my mind is we're running it very different than anywhere else. So at a full-scale plant, what the membrane manufacturers or warranty 3 to 5 years, correct? But they run it 100% of the time, right? And do clean in place. We're going to be running it for an hour a day. So we might get a lot more life out of it, or we might get a lot less. The other thing is I don't want to do a conventional clean in place. So Greg, one of my master students, part of his work is going to be understanding, hey, how can we actually clean this membrane with not citric acid and sodium hydroxide and all this other stuff? How can we clean it with something from the store? And maybe we do a different protocol than the membrane vendor recommends, because the idea with these membranes is that each home would be provided enough membranes to then install in their house, as well as give one to the co-op that the state is developing. And so when it fails, instead of cleaning it at their house or trying to deal with it, they take the whole housing and the thing to the co-op and say, I want my other one, please.
Well, yeah, home units, you just throw it away and replace it.
And so hopefully the co-op can clean it, and using maybe one of these techniques we come up with.
How much will this cost?
So our ticket price, ignorant of the state's surcharge, because I don't want to include it, is $80,000. The biggest thing that I want to highlight in there is that is including full labor derived from the community, as well as we're trying to design it with components that anyone can build. So we're not, the only laborers we're hiring to build this are the ones that plywood at the inside of our cabin currently. All of our fittings are like these sanitary fittings where I can take them apart in my hand and rebuild pieces of pipe, or I can push to connect fittings. So this shouldn't have to require anyone advanced to be able to do it. So the hope is that this is not an engineer or a contractor coming in from Anchorage to build it. This is training a community, shipping them to a community, the community doing it themselves, all from the ground up.
Do these communities have building codes?
They all have to abide by the plumbing, the universal, international? Uniform plumbing code. Obviously, I'm the academic in the room. Yeah, they all have to abide by that. Whether they do or don't it's hard to say. At least at some point, something's going to have to illustrate that it is, or it can be an amendment to it.
So once it's built, are you going to identify the weak links and kind of go from there and see?
Absolutely. So the way we have a 9-month schedule with the state that starts in July to do testing. Before the 9 months start, I hope to get a month to try to break it. That's what I do. And I've told all my graduate students that if you're not breaking stuff in the lab, you're not doing your work. So that's my first goal, is to try to find how to break it. And then we will, through this phase as well as through subsequent phases, if we're granted that, be identifying and correcting the weak links.
So how representative would it be of, rural conditions?
In Anchorage?
Those weak links.
That I don't really know. I think that we've experienced the same weak links as rural communities would so far, with ordering things and having them show up broken and trying to buy parts, and we're trying to do it the same way you would do in a rural community. We're not, we're ordering from the SBS rural catalog at times. Things like ultra cold temperatures, we're not going to be able to distinctly test. Although our take on that is if there's no water to freeze, then there's nothing to freeze. So we'll find the links, whether it's synthetically or when we have to freeze this system once during the study, we'll open the doors and let it sit out in the cold until it freezes.
Be careful of your membrane.
Yeah, Greg and I have talked a lot about the membrane. Hopefully, if you're leaving your house, you take your membrane to warm storage. 2 more minutes.
You mentioned the relatively low power demand except for heating the water.
Mm-hmm.
And I was curious if on your sleepless nights you ever considered the low voltage possibilities?
So, yeah, actually very much so. So all of the controls, all of the valves are all 12 volts. At this point, we have the ability to convert to 12 volts for our membrane pump and almost our entire system on here, except water heating in the washing machine. But again, I'm going after proof of concept, or I've been educated by other engineers to show that it works before you diddle around with optimization of that type of stuff. So it's on our agenda. We have a second Connex that was delivered by Shell that had a wind turbine for power generation. So maybe if it all works well, we can put a turbine on it later on. See how it goes. One of the ideas on that front that I didn't mention, the low voltage and the air. The bonus of having low voltage and air, I wanted to have a system that here in Anchorage, if the power goes out, you still have water. It may not be hot water, but you still have water at your house. So in this instance, and Village Power is mixed bag. Kayakuk, we were out there when they were doing a bunch of projects, and every day they would have a power outage. And so with the low voltage system, we're actually running a marine battery charger to 2 12-volt batteries, and the 12-volt batteries are powering all our fixtures. So as long as the batteries are charged, you're going to have all your fixtures able to function. The air is another nice thing. Our sewer water that's being air pressurized, the compressor is filling a tank. And we're running a tank at 100 PSI, but all our air systems are 15. So that tank being full when the compressor is off, now we have stored air to be able to move discharge water around too. So the house should survive, maybe not making water at this point because we're not doing a low powered or low voltage membrane pump. The house should be able to have a day or two not being connected to the grid and still provide water.
What prompted the question is my observation of rural areas, that unreliable village power you're talking about, that's a Cadillac
Yeah, agreed.
in rural areas.
Agreed. And that's the other reason why we wanted to be able to produce water quickly. So if you can produce all the water you need per day in 30 minutes, you're good. As long as you have 30 minutes of power. Hopefully. In Mexico, where I grew up, water cycled through the city. And so it was really fun taking friends down to Mexico because you said, hey, we're going to have water at this friend's house, but we're not having water at this friend's house. And yes, there'll be water, but they have a 300-gallon tank on their roof. And if you use it all up and grandma can't take a shower tonight, I see a belt in your future.
So are you going to include some alerts or information for the homeowners, like for low transmittance, if the stuff gets sudsy and can't see through it, or pressure differentials? Or...
Absolutely, but maybe not right off the bat. The nice part about using these little Motinos that are wireless is we can tell them to talk whenever they want. And so we're going to focus mainly on system operation first. And then likely next year, we're going to be adding in 2 computer science senior design groups to put interfaces to all of these things so that you could have a cell phone app that would tell you what's going on.
Your grade school are reprogramming your water system every night. What could go wrong?
Nothing, in my opinion. They'd have awesome water where they want it. All right.
Sisters in the shower. Let's fix it.
So you're welcome to come check this stuff out. I see people are kind of poking their head in the door, but thank you all for coming.